Right. So, good evening, everyone. Okay, welcome to the fifth live session for discrete mathematics. In case you were not present in earlier lectures, my name is Bhavya. I am a PhD scholar from IIT Madras. I'll be holding these problem-solving sessions every Tuesday, 6 p.m. Okay, so like always, I'll just go across briefly each material and then we'll dive onto the main questions. All right, so let us begin. So the topic for this time is functions, right? So last week we saw something called relations, right? Now, what are functions? Functions are just a type of relation. Function is nothing but a type of relation. What is a relation? You could relate two quantities. Okay, you could relate, for example, do A cross A, like, and A is consisting of 1, 2, and here 1, 2. Then A cross A would be like 1, 1, 1, 2, and so on. And we used to say like 1 is related to 1, 1 is related to 2, and so on. Now you can multiply several sets this way and create a bigger relation, right? And take a subset and so on. But function is a type of relation, okay, which we say that maps every element in A to exactly one element in B. Okay, this is what we call the set theoretic way of seeing functions. Okay, every element in A maps to exactly one element in B. What does that mean? It means a relation where one cannot be related to two items. Okay, it cannot be that one is related to one and one is also related to two. It should be something like this: one is related to one and two is related to two. Now this is a function. Good. Why? Because this is an element from set A, and let's say this is from set B, this is from set A, set B. One element is mapping to at most one element. We don't have one maps to two. Okay, one is mapping to one and two is mapping to two. So these kind of relations are what are called functions. But another way, this is a set theoretic way to view it. That is like, see if, okay, I'll show the alternative representation later. But see, this is the most popular way, okay, the high school way to look at functions. Okay, this is the most popular way to look at functions, which is like f maps from this natural numbers to natural numbers. It means this is my set A, this is my set B, okay. Or in other words, my function takes an input from this set and gives me an output from this set. And in this, very algebraic way of looking at it, functions can be thought of as a box where I can put an input and get an output. For example, f of x is written as x plus 1. So we can input any natural number, okay. So let's say I do f of 1. So f of 1 is 1 plus 1, which is 2. Now what is f of 2? F of 2 is x plus 1. So what is x here? 2. 2 plus 1, which is 3. And similarly, f of 3 is 4, and f of 4 is 5, and so on. Okay. And this is one way to see it. The set theoretic way to see it, and mostly in discrete maths, this is how we see it, functions, okay, is as follows. If I have a 1, okay, then it maps to a 2, right? F of 1 equals 2. If I have a 2, then it maps to a 3. So f of 2 is equal to 3, and so on. And 3 maps to a 4, and 4 maps to a 5, and so on. So this is a function in the set theoretic sense also. Why? Because it never happens that 2 or 3, okay, or 4, okay, maps to two elements at the same time. It cannot be that 4 maps to 5 also, 4 maps to 6 also. Something like this never happens. So this is an example of a function. Okay, so this is an example of a function. Now um, right, so one thing I'll show you. Okay, so okay, I'll anything that looks like this, oh sorry, anything that maps this way and that way, and let's say one, okay, not this one, let's say two elements, okay, let's say 1 2 3, let's say 1 maps to this element, right, let's say 4 also maps to that element. This is allowed in functions. But what is not allowed? 1 maps to this element, and again 1 maps to another element. Right. So something like this is not allowed. This is the problem. So this is not a function, and this is the function. Now in the lectures, okay, I'll just briefly tell you. In the lectures, you may have seen something, and in the yeah, if you look at this function, okay, fx equals x plus 1, you will see that okay, if I take the natural number to start from 1, okay, you'll see that nothing maps to 1, right? So but this is the set of natural number, right? So this entire thing is what is called the codomain. But whatever, the smaller set that we can map to, okay, this is called the range of the function, whatever we can map to, okay. And the bigger set where we may or may not completely cover, okay, that is called the codomain. And this, wherever we take the elements from, which is nothing but natural numbers, is what is called the domain of the function. So domain is where we take inputs from, and codomain is where we give the outputs to, okay. Or in simpler words, this is the domain, this is the codomain. But you observe that the entire codomain may or may not be covered, right? For example, here nothing will map to 1, and it's a function, that is no problem, but nothing will map to 1. So it seems like this function will give outputs to only these everything except 1, right? It will map to all the elements except 1, assuming that natural numbers start from 1. So therefore this actual set where we map to is what is called the range. Okay. Yeah, now that is enough introduction to the preliminaries of functions. We'll look into detail later. First, we'll just solve this simple question. All right. So yeah, so the first question, let's look at the first question. The question says the following: determine whether f is a function from integers to real numbers. Okay. Now the first question says f of n equals plus minus n. So let us just plug in some values. Okay, we are talking about integers. So what does integers mean? Like integers is nothing but minus 2, minus 1, 0, 1, 2, and so on. Positive numbers, negative positive natural numbers, negative natural numbers, and 0, right? These are integers. Now if I plug in an f of n equals, okay, sorry, if I do say n equals 1, or let's say 0, then f of 0 is equal to plus minus 0, which is nothing but 0. But say n is equal to 1, then f of 1 equals plus minus 1. So what does plus minus 1 mean? It means plus 1 also and minus 1 also, right? both plus 1 will satisfy this and minus 1 will also satisfy this, which means that my function is mapping to two, f of 1 is mapping to two different outputs. So this is clearly not a function. I hope it is clear. So if this is my set, let me make a bigger one. So on -2, -1, 0, 1, 2, and so on. Okay, 1. Okay, 0, -1, -2, 1, 2. 0 will map to 0. 1 is mapping to -1 also. 1 is mapping to 1 also. So this kind of thing is not something we would expect out of a function. So this is not a function. Okay. So right. So again, so can you tell me what b would be like? Is b a function from integer to real numbers? F of n equals root n square plus 1. So would this be a valid function from real number to integers? Oh, sorry, integers to real numbers. I'm sorry. Stuti says it's function. Akanksha says true. Okay. Well, so let's try it. Okay, Divya also says true. Okay. Oh, okay. Let's see. So, well, one doubt that may always be that, okay, we need to map to reals. Okay, the output needs to be a real number, but we have a fear that, okay, it might be imaginary. How do we encounter a case when there is a negative sign under a root? But can we really encounter a negative sign under the root? No, right? Because if I put, let's say, f of -1, okay, -1 is an integer. So what is this? This is root over, okay, 1 -1 square plus 1, which is nothing but root over, okay, 1 plus 1, okay, and minus becomes positive, and obviously for the case of positive number, this under the root it will be positive, and for the case of 0, root over it will become 0 square plus 1. Again, you have a positive number under the root. But an important thing is that how the square root function behaves in terms of integers. Okay, in terms of integers, we know that I can find square root of a number in two ways, into integers in two ways. We do write that, okay, 16 equals root 16 equals 4, but this is in the case of natural numbers, right, or positive integers. But if we allow negative integers, root 16 is equal to plus minus 4. That is, 4 times 4 is also equal to 16. So minus 4 times minus 4 is also equal to 16. So negative 4 also qualifies as a square root in terms of integers. And we are talking about reals here, and reals also contain the integers, right? So therefore, if I look at the mapping, we go from -2, -1, 0, 1, 2, so on. And here what do? You go from let's say there is a -4 here, okay, so -4, -3, -2, -1, 0, and so on till 4 here, okay, okay, 1, 2 here. If I do is it from integer? Yeah, okay, so if I choose 4 from here, okay, if I try to map this, 4 will map both to -2 and to 2. or actually it's n square plus 1. No, we can't even go with 4 actually. Needs to be some square root plus 1. So a direct example cannot be given, right? But anyway, an n square, a number which is of the form k square plus 1 will map to a, okay, it will map to two numbers. Will map to two numbers. Okay, it'll map to plus root k square plus 1 and minus root k square plus 1. So it's mapping to two different numbers, right? So this is clearly not a function. I hope that is fine. It is not a function because it maps to two different places at the same time. Okay, now, okay, okay, yeah, let's try this one. F of n equals 1 by n square minus 4. Okay, hello. F of n equals 1 by n square minus 4. This is not a function. Okay, others? Okay, let's analyze this case. Okay, so for the case of n equals, if I do n equals 0, then f of 0 equals 1 by minus 4, which is minus 1 by 4. Is this real? Yes, this is a real number. And let's say n equals 1, then f of 1 equals 1 by 1 square minus 4, which is 1 by minus 1 minus 4, which is minus 1 by 3, which is again a real number. And we can go on now. We can go on to, let's say, equals 2. Okay, n equals 2. Now what do we have? You have f of 1, which is equal to 1 by, okay, now n square minus 4, which becomes n square is 4, okay, minus 4, which is undefined. Okay, and which is infinity, and infinity is not a real number. Infinity is not exactly a real number, right? This is undefined. We cannot tell anything about it. So yes, this is not a function. That is correct. But like if we ignore this case, okay, if we ignore this case, then we can still say that, okay, then we can say that, okay, anything greater than 3, this will be fine. We are fine with it. yeah, anything greater than equal to 3, we are fine with it. If that was given to us, then yes, we would have said this is a function. But we see that, it fails in this case. So through the set theoretic definition, this is not exactly a function. Okay, so this is not a function, right? Okay, good. So now the question, okay, another simple set of questions. Okay, someone is here. Okay, another simple set of questions. So we are saying find the domain and range of the following function. Okay, f of xy equals max of xy where x and y are positive integers. Okay, always remember, like I said, if this is the domain and this is the codomain, range is whatever the domain can map to. Okay, remember this diagram. This is the range. The question says find the domain and the range of the following functions. F of xy, okay, is equal to max of x comma y where x, y are positive integers. Okay, now yeah, f of xy takes the maximum between x and y. So what is the domain? Domain is set of inputs for function f, right? It is where we take the inputs, but we see here that f actually does not take a single input. It takes two inputs. So it takes a tuple. If we remember the relations chapter, okay, it takes a tuple as input, two numbers at once. So if it takes a tuple, then what is the set that it takes from? It takes input from a Cartesian product of two things, and x and y are what? Positive integers, right? So it takes input from positive integers cross positive integers, right? So what do positive integers cross positive integers look like? It's something like 1 comma 1, 1 comma 2, and so on, and 2 comma 1, 2 comma 2, and so on. If you take the cross product, it will look like this, right? These are exactly my inputs because both are positive, right? X and y are positive integers. And what does it give? Output. If the input is maximum between x and y, output will also give you some maximum. Output will also give you a positive integer, right? Output will also be positive integer. So if output takes elements from, it gives you an element from the set of all positive integers, your range, okay, will be exactly that. Thus, so this is your domain, okay. Range of f, function f, equals the set of positive integers. So you can see it in this way, like for example, max of 1 comma 2 equals 2, max of 3 comma 4 equals 4, max of 3 comma 3 equals 3, and so on. It takes elements from this Cartesian product between positive integers, sets of positive integers, and outputs always positive integers. So this set will comprise the range, and this set will comprise the domain. Okay. Okay, I think. So let's look at the second one. Okay. F is a function that assigns the next largest integer to a positive integer. So can you tell me whether this is you know so what is the domain and range here? F is a function that assigns the next largest integer to a positive integer. For example, like um, f of 3 equals the next largest integer is 4, f of 56 equals 57, f of 32 equals 33. It just adds 1 to it. So can you tell me what is, okay, just tell me what is the domain here? So what is the domain in this case? In 2b. Okay. Okay, I'll do it here. But I hope everyone is following me. I do not hear any responses over. So I hope I did not lose anyone in the way. Okay. But please stop me and let me know if there are any doubts. Okay. Yeah. So the question says f is a function that assigns the next largest integer to to a positive integer, right? So we know that it takes an input as a positive integer. F takes input as positive integer. So f takes an input from the set of all positive integers in other way. So therefore, you know, the domain is the set of positive integers. Or you can also write it as, you know, all the x such that x belongs to z and, you know, x is greater than 0. So next thing is we need to find the range. Okay. Now see, if I take any output of the function, I can go back to the input. How? For example, I'm saying if I am given 4, okay, and I tell you like what was the input such that f give 4, I can also always do 4 minus 1 and get 3. Similarly, I can always do 57 minus 1 and get 56, right? So 4 goes to 3, and you know, and anything above 4 I can do the same thing, and 3 I can say that, oh okay, 2 was the input for 3, and 2 I can say okay, 1 was the input, but for 1, okay, I cannot say that 0 was the input because 0 is not a positive integer, but my domain is only this many, so I cannot go back. So 1 lies outside the range. In other words, if I make it diagrammatically, okay, if I do this, okay, and I do a 1, 2, 3, 4 and so on, these are the positive integers, and here I do 1, 2, 3, 4 and so on. 1 maps to 2, 2 maps to 3, 3 maps to 4, 4 maps to 5 and so on, and everything below it will get covered, and this one is left out. So this is my range. Although, we map to all positive integers, this is my codomain and this is my domain. Okay, so range equals 2, 3, 4, 5 and so on, which is nothing but all the x such that x is a positive integer and x is greater than or equal to 2. This is my range. Okay, I hope it is clear. Okay, so let's look at this one. F assigns the last digit to a positive integer. So can you tell the domain and range? So domain, like before, domain is pretty clear, right? You take all inputs from positive integers and you are done. And this is your domain. So you take only positive integers and that is the set of positive integers is your domain. But what is the range here? 0 to 9. Akanksha is 0 to 9. That's right. So that's right, Akanksha. But the answer is 0 to 9. Well, why? I mean, domain is like before, positive integers. Okay. Now, if it says, the function maps the last digit to a positive, assigns the last digit to a positive integer. For example, if I have, f of 1 equals 1, f of 2 equals 2 and so on, f of 32 will assign the last digit is equal to 2. F of 45 is equal to 5 and so on. So, this, since we are talking about digits, okay, since we are assigning it as digits, a single digit cannot be more than 9. No? So this is maximum 9. Any digit is maximum 9. And any digit can even take the value 0. For example, 4040, which is equal to 0. F of 40 is 0 because the last digit is 0. So a digit can range from 0 to 9, which means that range is equal to 0, 1, 2 and so on till. Okay, I hope it's clear. Now another simple question. Okay, consider the function defined as follows: f of x equals x plus 7. Okay, for the function, write the domain, codomain, range, preimage of 53. And the domain and codomain are already given in the question if you see carefully, right? So what is domain? This is the domain and this is the codomain. So A's answer is set of natural number and B's answer is set of natural number. But now what do we need to find? The range. What is the range? As before, I think now you've got the idea of it, general idea of it. We just want to see, what are the possible mappings out here. What are the possibilities that will map to? So, for example, it takes all the f takes all the natural numbers, right? So if it takes all the natural numbers, assuming natural numbers starting from 1, so 1, 2, 3, 4, 5 and so on, and here too 1, 2, 3, 4. Divya says range is x belongs to s so that x is greater than or equal to 8. Right. Okay. That's right. Good. 4, 5, 6, 7, 8, 9, 10, and so on. Okay, this is my set. So 1 maps to, okay, f of 1 equals 1 plus 7, which is equal to 8. F of 2 equals 2 plus 7, which is equal to 9. F of 3 equals 3 plus 7, which is equal to 10, and so on. Now we see the pattern, right? So f of 1 maps to what? 1 maps to 8. F of 2 is equal to 9. So 2 maps to 9. And 3 maps to 10. And 4 maps to, and so on. And we realize that starting from 8, we never miss any number here. We'll map to every number. So what are the guys who are getting left out? The people who are getting left out are here. So these are not getting mapped to. Who are getting mapped to? These people. So this is exactly the range, the actual people that you are getting mapped to. And the range of f of my function, okay, consists of, yeah, like Divya said, all the elements such x such that x is a natural number and x is greater than or equal to 8. Now the question asks, what is the pre-image of 53? Okay, I do not use this term. I did not explain it before, but I'll quickly tell you now. But I think it's there in the lectures also. So a pre-image is the reverse of the function, or more correctly, the inverse of the function. So if 1 maps to 2, f of 1 equals 2, then pre-image of 2 is 1, or it is also written as inverse f inverse of 2 is equal to 1. So f inverse, this thing, imagine it as a function going back. So therefore the question is saying pre-image of 53, which is nothing but f inverse of 53. And what maps to 53? Let's say 53 was mapped to some f of x. And what is f of x? 53 equals x plus 7. Right? F of x is x plus 7. So this means that x equals 53 minus 7, which is 46 is the answer. We'll use this pre-image notion later also. Okay. Oh yes, Suti has written 46. Good. Right. Yeah, I hope everything is clear so far. So yeah, let's move on quickly. Types of functions. We've seen it in the lectures. 1-1 functions. Okay, we can, by the behavior of how they map, we can segregate into different types. 1-1 functions are technically defined this way. Okay, if f is a function that maps from set A to set B, it is called 1-1 if for every y in B in the second set, that is, okay, wherever we are getting mapped to, the inverse, okay, the people who map to it, okay, the people who mapped to y is less than or equal to 1, at most 1 people. That is, f of x is unique. Okay, it could be 0 also. Note that this means that f inverse could be 0 also. That is, no people mapped to it. Or in other words, diagrammatically, this is what 1-to-1 or 1-1 function looks like. 1 maps to just 1. Okay, a non-example would be this way: 2 functions mapping to the same, 2 inputs mapping to the same output. Okay, this is a non-example of a 1-1 function. But see, look at the case that some items may get left out also, but that is all right as long as 2 inputs do not map to the same output. It is fine. Okay. Okay, onto function f maps from a to b is onto f for every y in b, means in the output. Okay, the people who map to y, f inverse of y is greater than equal to 1. Okay, it could be 1, but it's greater than equal to 1. Now the key idea is for every. Okay, that is all elements in b are covered. This is another way to see onto functions. Onto functions simply means that every element in B can be mapped to from some input in A, which simply means, okay, whatever it gets mapped to is called the range, right? But we are simply saying that it gets mapped to all the elements in the domain. So the domain, sorry, not the domain, the codomain is equal to range. This is when we say a function is onto, everything gets mapped. Recall that it was not the case in the case of 1 1. Everything did not get onto. But also see that you can have these kind of things. You can have oh, okay, sorry, this is not a proper example here, right? So okay, so you can see that this is 1 1 also, this is onto also. Yeah, so this is 1 1 also, this is onto also. But if there was one element and it mapped to this, it would not be 1 1. Okay, but it is still onto because all the elements are getting covered in the set B. Now what is bijection? A bijection is a function is called a bijection if it is both 1 1 and onto. Both 1 1 and onto, meaning 1 1 meaning that two outputs cannot map to the same input. Okay, and onto meaning that everything gets covered in the second set. Okay, so yeah, I hope this quick recap was fine. We'll move on now. Okay, the question is saying the following: define a function f and g, okay, which maps from a to b as follows. F maps a to b, b to a, c to c, d to d, and G maps A to B, G maps B to B, C to D, and D to C. Now we want to check the conditions. This is F11 but not onto, G is neither 1 1 nor onto, F is onto but not 1 1, and so on. So which of these options are correct? Okay. So first let us try to do it diagrammatically. Okay, and later questions we might try to do it in a more formal way. Because the set is very small, we can just do it diagrammatically. It won't be a problem. So both take values from A, B, C, D. Okay, A, B, also sorry, this should be A. Yeah, C, D, A, B, C, D. So f of A is B, so A maps to B, and f of B is A. Okay, C is C, and D is D. This is function f. So what do we observe here? We observe that is it 1 1? Yes, it is 1 1 because something like this is not happening. Two inputs mapping to the same output like this is not happening. So this is 1 1. Is it onto? Yes, it is onto because all the elements in the right side are getting covered. All the outputs are getting covered. Okay, it is onto. Um, let's see G. Let's try G. Okay. G says okay. Let's first fill in A B C D A B C D. G says the following: A maps to P. G of A is equal to P. Next, G of B equals B. B maps to itself. Okay. And G of C equals D. And G of D equals C. So G of B equals B. Yeah, okay. So I think there's something wrong in the option. Okay. Anyway, here do we check whether this is 1 1 or not? Okay. Is this element 1 1? No, it is not 1 1 because this exists. Right. G of B equals B. Yeah. So this causes it not to be 1 1. Is this onto? Well, onto requires everything in the right side to get mapped to, but A does not have an inverse here. Okay. So therefore, it is not onto also. So it's neither 1 1 nor onto. Okay. And should not be F is 1 1 but not onto, but it should be F is 1 1 and onto. Okay. So yeah, F is 1 1 and onto, but G is not 1 1 not onto. Okay. So yeah, let's look at the next question. Okay. Next question says f of n equals n minus 1. Which of the following are 1 1 onto or both? So can you tell me for A, f of n equals n minus 1? Can you tell me it maps integers to integers? Okay. Is it 1 1 onto or both? F of n equals n minus 1. Is this 1 1? Is this onto? Is it both? Akanksha says 1 1 and onto. Okay. Okay, good. Kumati also says both. Okay. Okay. Yeah, Gomti Akanksha, you are right. This is both 1 1 and 1 2. Okay. The key thing is that we are mapping from integers to integers, so it could be negatives and positives both. Now, so first let's get an idea about what this function looks like. Okay. So yeah, 0 0 1 1 2 2 minus 1 minus 2 minus 2 minus 1 and so on. So these are both set of integers. So 0 maps to 0 minus 1, which is minus 1. Minus 1 maps to minus 1 minus 1, which is minus 2. And 1 maps to 1 minus 1, which is 0. 2 maps to 2 minus 1, which is 1. And so on. So we can already see what is happening here. We already see that it cannot be that two items map to the same input. That is it 1 1? From the diagram it looks like it is false. Okay, but how do we formally show this? Okay, we formally assume okay, let's say two elements mapped to the same output. That is, let's say f of n1 equals f of n2. Two, integers mapped to the same output. Then what we do is f of n1 equals f of n2, which is nothing but n1 minus 1, which is equal to n2 minus 1, right? And then we'll cancel this off, and then we've got n1 equals n2. So what we assumed that n1 and 2 could be different is wrong. n1 should always be equal to n2, right? So if such a case arises, if two outputs map to the same input, it can only be that the two outputs were if two inputs map to the same output, it can only be that the two outputs are actually same. Two inputs are actually same. So yeah, it is 1 1, right? And is it on 2? Yes, it is on 2. Every element has an inverse. You can go back every element. If it did not have an inverse, okay, for example, if one element were not mapped to, okay, if it did not have an inverse, then it would mean that this element was left out. But it happens so that you can get every element from it. For example, like if if output equals y, then if output equals y, then I can always do y plus 1 equals n, or in other words, this is f of n, right? So y equals f of n is n minus 1, and n equals y plus 1. And what is y? Y is the input corresponding to this, right? So which is nothing but the inverse. Okay, so yeah, you can always do that. You can always come back from each element, which means that every element was actually getting mapped to. So there is no element here which is getting left out. So yeah, the part B, can you try? Can you try part B, whether f of n? Okay, Akanksha is neither 1 1 nor 1 2. That was quick. Just 1 moment, I'll charge my laptop. Yeah, Divya also says neither 1 1 nor 1. 2T also says neither 1 1 nor 1 2. Good. Okay, we have 3 people saying. Okay. So can I hide this? Note. Yeah, good. So B is the following. B is f of n equals n square plus 1. Is this 1 1 or 1 2? So let's look at 1 1. So 1 1 meaning, like, is it true that every two elements will map to the same thing? So this reminds us about the previous previous case when we were talking about positive and negative integers. So we realize that if n equals 1, then f of n equals 1 square plus 1, which is equal to 2. Now if n equals 2, and okay, we are not interested in n equals 2, let's say n equals minus 1, then f of n equals minus 1 square plus 1, which is equal to 1 plus 1, which is equal to 2. So thus we have a case like this to the same element. So this is clearly not on 2. It's clearly not 1 1. Good. Then next is asking on 2. Is it on 2? Are all elements getting covered? That is what we are saying. But n square plus 1, that's what they are saying, right? So take this will only do some, perfect square plus 1. So if we look at, f of 1, then it is 1. F of 2, it is f of 2, it is 2 square plus 1, which is 5. F of 3 equals 3 square plus 1, which is 10. And you can already see that, we are actually leaving out some things in between. For example, 2 does not feature here. 2 does not belong here. No input will give me 2. How can I say that? Well, 2, let's say 2 was an output to some input x. Okay, let's say it was an output to some input x. Then x square plus 1 equals 2. That is what it is, no? Yeah, n square plus 1. So x square plus 1 equals 2. X equals 1. Okay, x equals 1. And x equals 1. And x equals plus minus 1. Oh, okay. So 2 actually features here. Okay, let's choose 3. Okay, now my claim is 3 does not actually feature here in this list, because I think f of 0, okay, 1, f of 1 equals 2. Yeah, f of 1 equals 2. That's right. Sorry. F of 1 equals 2. So 2 is actually a good example. It's not a bad example. So 2 so we want a bad guy, right? For example, 3. I claim that 3 does not appear in the who was that? I think it was Gomati, right? Yeah, Gomati. F of 1 equals 2. Yeah, good. Sorry. So let's talk about 3. My claim is that 3 does not appear here. Well, if 3 were to appear here, okay, say f of x equals 3, some output, some input will give 3, okay, as output. Then x square plus 1 equals 3. Then x equals 3 minus 1, which is 2. X square equals 2, which implies x equals root 2, or plus minus root 2, however you want it. Now what is plus minus root 2? This cannot be an integer, right? But we want our domain, our codomain is giving us integers only. So we can never find a partner for, this x, to map to. Or we can never find a 2 to get mapped to. 3 to get mapped to, sorry. 3 will stay lonely. 3 cannot get mapped to because, there is no integer that will map to it. There is only a real number that will map to it. It is real, right? But here we had, only integers. The left set was integers, right? So therefore this is not on. Okay. Okay, we'll leave out D. Can you quickly tell me Fn equals n cube? Is this 1 1 or 2 or both? D we might have to leave out due to interest in of time. Akanksha says 1 1 only. Okay, Divya says both. Divya says both 1 1. Gomati Sankhara 1 minus 1. Oh, okay, 1 1. Okay. Yeah. Gomati said 1 1. I read it as 1 minus 1. Okay. F of n equals n cube. Okay, let's see who's right here. Okay, um, so f of n equals n cube. Let's check if it is 1 1. Okay, how do I check whether it is 1 1? Well, I can like diagrammatically try to see it, but more formally and a foolproof way to check it is, like I said, assume that two elements, map to the same output. Let's say they are different. Let's say let us contradict ourselves. Okay, let's say two elements are different and they map to the same output. Then what do we have? F of n1 is n1 cube, and f of n2 is n2 cube. Right now, by the powering law of arithmetic, if we have integers to the same powers, it means that the bases are also same. That is, if this is like a high school rule that x to the a equals y to the a, this means x equals y. Right, they have the same powers, their powers are equal, meaning they are same. This means n1 equals n2, therefore 1 1. Good. Now next part, is it on 2? That is the question, right? I think there is where the conflict of interest is happening. So, well, again, if I observe the diagram, okay, 1 will map to 1 cube, that is 1. 2 will map to 2 cube, which is 2 fours, okay, 2 cube is 8. And 3 will map to 3 cube, which is 27, I believe. And 4 will map to 64 and so on. And there are places here which I'm not sure whether they are there in the list or not. So for example, if I take take a small number, let's say 3 here. Okay, let's say I take a 3. My question is, does 3 appear in the list? Does 3 get mapped to? So let's say 3 does get mapped to, say f of n is equal to 3, then n cube equals 3, right? Then, and this means that n cannot be integer. We don't know any integer such that its cube maps to 3. Or you can even simplify it this way, that n to the no, so that cannot be done. Yeah, n cannot be an integer, so n should be real. But we wanted an integer, right? Because on the left hand side I can take inputs only from integers, and therefore it is not on 2. So this 3 is an example of a number which does not get mapped to at all. Okay. So we'll skip the D part. Okay. And yeah, let's do more on bijections and so on. So remember that bijections are those functions which are both 1 1 and 1 2. Okay. Question says the following: what is the, okay, let A and B be two sets such that size of A equals size of B, which is equal to 5. What is the number of possible bijective functions from A to B? Well, in the lecture, I think a direct formula was discussed and its explanation. Well, you don't need it also per se, but yeah. Um, there's a straightforward formula to do this. If you recall the formula, then please try it. If you don't recall the formula, then try to think of it logically. How it's a simple counting argument. Okay, Akansha 5. Okay, Akansha give the formula away also. Good. Yeah, it's 5 factorial. Okay. Everyone else? Okay. Um, yeah. So see the answer. Okay, the number of possible bijective functions. Okay, given two equal cardinal sets. Okay, is the cardinality factorial, or let's say if a the size of a equals n, then it is n factorial, which is 5 factorial here in this case, which is 120. So answer is C. But I can quickly even tell you, it is there in the lectures actually, but I can even quickly tell you how this formula came to be. Take these two sets which are equal in cardinal, and by the way, bijections can only exist between sets of equal cardinality. It cannot be one set is bigger, one set is small. It won't work that way. So, and there are 1 2 3 4 5 elements here, and 1 2 3 4 5 elements here, and I want to do a one-to-one mapping, and also I want to cover the entire set. So for one, if I want to map, how many choices do I have? 1 2 3 4 5. I have 5 choices, correct? Now let's say I choose this choice. For 2, how many choices do I have? For 2, I cannot map to 1, because as soon as I map to 1, this function stops being a bijective function, because it will stop becoming a 1-1 function. So we only have 4 choices left now. The 4 choices left are 2 3 4. The 4 choices left are 2 3 4 5. So how many? Okay, wait. So 2 3 4 5, which means I have 4 choices here. So 5 times 4, and then I'll map 2 to, let's say, 3, and then I'll have 3 choices left. Then I'll have 3 choices and 2 choices, 1, which is equal to 5 factorial. So this is another simple way to look at it. Okay, this is actually a proof to this particular argument. Okay. So yeah, another one. The number of 1-1 functions from a set A to B is 60. The set B has 5 elements. What is the cardinality of set A? Okay. So this might be slightly more challenging. Okay. There is a direct formula also, and it was also done in the lecture, I think. Okay. The number of 1-1 functions from a set A to B is 60. Okay. These are the different functions I can create from A to B, which are 1-1. And I'm given the cardinality of the set B. I'm told set B has 5 elements. What is the cardinality of set A? Any idea now to solve this one? Okay, I'll do it halfway. Okay, and then I'll just tell you this way. Okay, number of 1 1 functions from A to B is size of B, that is cardinality of P, P size of A, where P is that permutation. Okay, now I think it becomes fairly straightforward to solve. Number of functions is given as 60 for us in this case. Okay, then I guess I'll solve it here. So it was done in lectures. This is also a counting argument, okay, that this is the number of 1 1 functions. Okay, it's a nice argument. You can see it back in the lectures. But now how do we come to solve these questions? Okay, the number of functions, 2T says 3. Yeah, good, Suti, that's right. The number of functions is equal to 60 for us. Number of 1 1 functions is equal to 60 for us, which is our B permutation A. Right. Now 60 is equal to the size of B permutation size of A. Right. And this means 60 is equal to, just open up the into formula of permutation, 5 factorial divided by 5 minus cardinality of A factorial. This is what we have. Okay, now 60 equals 5 factorial. What is 5 factorial? 6 for the 24, 120. 5 factorial is 120 divided by 5 minus size of A factorial. So 60 once, 60 twice is 120. So 5 minus A whole factorial equals how much? 2. Now this question is logical. What factorial will be equal to 2? Okay, what factorial will be equal to 2? The answer is there is only one number whose factorial is equal to 2, and that is 2 itself, right? 2 into 1 is 2. So 2 factorial is equal to 2. There is only one such number. So it means that 5 minus size of A equals 2, which means that size of A equals 5 minus 2, which is equal to 3. So the answer is option C. Okay, I hope everything is clear. So by the formula given in the lectures, okay, the number of 1 1 functions from A to B is what? Size of B permutation size of A. Now what we did was, we are given the number of 1 1 functions, okay, which is equal to 60. 60 is equal to, by the formula, size of B times permutation size of A. We open up the permutation and simplify, and finally we get this term. And there's only one one number which will give us 2 when we take its factorial, and that is 2. And simplifying, we get that the size of A was actually 3. Okay, good. So we are done with that. We'll do 3 more questions here. 3 more questions are left, then we'll call it day. Okay. Composition of functions, and this was to the near towards the near of end of the lectures. Composition is like putting one function into another. Okay, it's like putting one. Before I talked about thinking of functions as a box, right? So this is thinking of functions as a box within another box. Okay. So, or you can also think it as a box followed by another box. Yeah, this is a more natural way to think about it. So F composition G, okay, I call this composition, is equal to F of G of X. For example, if F of X is 3 of X square, G of X is 4x plus 2, F composition G of X equals F of G of X, okay, which is equal to F of G of X. Now what is G of X? 4x plus 2, right? I'm simply substituting G of X here. Now what is F of 4x plus 2? We need to do 3x square, 3 and input square times 4x plus 2 whole square. We are plugging in 4x plus 2 as the argument here, as the input here. Okay. So yeah, so this is my F compose G of X. Okay. Or a simpler another example is 2x, G of X is 3x square. Okay, so this time let's do G compose X, G compose F of X, which is G of F of X. What is F of X? 2x, that is so G of 2 of X, G of 2x, which is equal to, now I put 2x instead of x as the input here. Okay, so it is 3 of 2x square, which is equal to 3 times 4x square, which is equal to 12x square. So composition of two functions will give me another function. Okay, so yeah, I think these examples are enough. Now another just a simple question to make us familiar with this notion. F of X is 5x plus 1, G of X is x cube. What is G compose F of 3? What is G compose F of 3? Let me show this here. Yeah. Akanksha says D. Stuti says 4096. Oh, okay. Same D. Option D. Right. Good. Yeah, that's correct. So, well, the idea is simple. So, we need to find G compose F of 3. G compose F of 3 is equal to G of F of 3. Right. Which is equal to G of F of 3. What is F of 3? 5 times 3 plus 1. See, I'm taking it from the definition of F. I'm taking X as 3 here. Okay, I'm taking the input as 3 here. So 5 times 3 plus 1, which is g of 16. Now, what is g of 16? By definition, g of x is x cubed, so g of 16 is 16 cubed simply, which is equal to 4096. So answer is B. Good. Yeah, that was correct. I hope everyone else is also convinced. Composition just talks about taking the output of one function and plugging it in as input to another function. For example, in this case, the output of f of 3 we gave it as input to g, and then the output of this g was the output of the entire composition. Okay. Yeah. Okay. Can you look at this question? The question says let a equals 0, 1, 2, 3. Okay. F is a function from a to the same set A. Okay. Defined as f of x equals x plus 1 mod 4. Okay. X plus 1 mod 4. So how does this mod work? Okay. Mod simply means remainder on dividing by 4. So for example, 5 mod 4 would be 1, right? Because 4 leaves the remainder 1. So 8 mod 4 would be 0, because dividing 8 by 4 will leave a remainder 0. Similarly, 11 mod 4 equals 3, because on dividing 11 by 4, okay, 4 2 is 8, will leave a remainder 3. So just mod 4 just represents remainder on dividing by 4. Okay, so x plus 1 mod 4. So see, this does not mean that the mod is on 1. Okay, does not mean the mod is on 1. The mod is on x plus 1 as a whole. So to remove the confusion, I'll put a bracket here. Okay, so fx equals x plus 1 mod 4. What is f compose f? Is it neither 1 1 nor onto 1 1 but not onto, both 1 1 and onto but not 1? Can you tell me which of the 4 options are true? Akansha says both 1 1 and 1 2, right? Yeah, D, bijection. Okay. Okay. Anyone else? Okay. Yeah, that's right, Akansha. In fact, I mean, this is a field of mathematics called permutations. Okay. And so yeah, f is a type of permutation. Anyway, good. Yeah. So the answer is D, both 1 1 and 1 2 bijection. Okay. Why is it a bijection? Well, since my set is very small, I can even solve it diagrammatically. I don't need any complex arguments for this. Okay. So 0 1 2 3. 0 1 2 3. So f compose f, right? I need to find f of something x. Okay, is this function bijection? That is what we are asking, or 1 1 1 2, whatever. So 0, okay, f of 0 equals 0 plus 1 mod 4, which is equal to 1 mod 4. On dividing 1 by 4, I get a remainder 1, which is nothing but 1. Right? So 0 maps to 1. Now 1 maps to f of 1 equals 1 plus 1 mod 4, which is 2 mod 4, which is 2. On dividing by 4, I get 2. Right? Similarly, 2 plus 1 mod 4 is 3 mod 4, which is equal to 3. Now f of 3 is equal to 3 plus 1 mod 4, which is equal to 4 mod 4, which is equal to 0. Because on dividing 4 by 4, I get a 0. I get this. So far, I see that this is a bijection. 1 minute. Yeah. Okay. So far, I see that this is a bijection because every input is mapping to only one output, and all the elements in the right hand side are getting covered. Right. Good. But this is only one step. I need to find f of x. This is only f of x. Right. So if I want to find f of x, then I do this operation once more. Okay. I do this operation once more. 0 maps to what? Similar as before. 0 maps to 1. 1 maps to 2. 2 maps to 3. And 3 maps to 0. So this is f of x. So what do I have? 0 maps to 1 and 1 maps to 2. Okay. And 1 maps to 2, 2 maps to 3. And let's use another color. Let's say 2 maps to 3, 3 maps to 0. Right. And let's use orange maybe. 3 maps to 0 and 0 maps to 1. So what does this mean? This means that I can write it this way. Zero, 1, 2, 3, 0, 1, 2, 3. 0 maps to 2. 0 maps to 2. 1 maps to 3. This green line. I am removing the intermediate step. 1 maps to 3. 2 maps to 3. 2 maps to, oh no, not 3. 2 maps finally to 0, right? 2 maps to 0. I'm removing this this middle part, if in case you're wondering. And 3 maps to 1. 3 maps to 1. So now the question is it 1 1? Yes, it is 1 1. Why? Because each element is getting mapped to only one element. Each element in the right is getting mapped to by only one element. Right? Two elements are not coming in, like this. This kind of thing is not happening. So this is 1 1. And is this on 2? Well, all the elements in the right are getting covered. So this is on 2. Okay. So yes, it is a bijection. Answer is D. Yeah. So was it Akanksha? Yeah, Akanksha is D. That's right. Good, Akanksha. Yeah. So I hope it is clear. Okay, so the key takeaway of this question is that, think of composition of functions as nothing but um, nothing but several steps, but still they are finally a function only. So this is equivalent to this. I'm removing the intermediate step here. Okay, so in case you do not understand, please let me know. We just have one question left. Okay. Okay, let's move on. Please let me know, okay, if there was anything. The questions is the following. Okay, this is the final question. Consider the function 1 2 3 4 5 which maps to 1 2 3 4 5. Okay, question is, how many possible functions f are there such that size of f inverse of 5 equals 3? This could be slightly more thought provoking. Please give it your hand. Okay, try to think about this question. Consider the function this which maps f from one set of 5 elements to another set of 5 elements, the same set of 5 elements. How many possible functions are there such that f inverse of 5 is equal to 3? Okay, you may need to use the fact that it was done in the lectures in the beginning that number of functions. See, I'm not talking about 1 1 1 2 or anything. I'm just saying number of functions from a to b is equal to size of a to the size of b. Oh, sorry, size of b to the size of. Anyway, this you might need it towards the later part of this question, but you just think about it for a moment. You maybe try to draw similar diagrams like I did just now. What is meant by um, f inverse of 5 equals 3? It means that 5. There are 3 elements, okay, that map to 5. Because f inverse of 5 would be like 1 2 5, and 1 maps to 5, 2 maps to 5, 5 maps to 5. There are 3 elements that map to 5. So so this is more of a counting question. Okay, I'll proceed. Okay, so this is more of a counting question. Let me show it diagrammatically. 1 2 3 4 5. 1 2 3 4 5. Okay, and I'm saying how many possible functions f are there such that f inverse of 5, the size of this set, is equal to 3. Now f inverse 5, I mean, it need not be a single element. No, it can be a set of elements, because we know in functions that several number of people can map to the same element. For example, these three, if they map to 2, f inverse of 2 will be 1, 3 and 5, whatever will map to 2. Similarly, they are saying f inverse of 5 is 3, which means three elements that three elements are there that map to 5. For example, 1, 3, 5 could map to 5, or 2, 3, 4 could map to 5, or 4, 5, 3 could map to 5. Right. So such cases may happen. You need to count those cases. So I need to, in other words, I need to choose the elements which map to 5. So number of choices okay, for 3 elements to map to 5, okay, is from this 5 element set. I'm choosing just 3, any 3 here, or this 3 or something like that. Number of choices, we know that it is 5, choose 3. Right. Now let's say I chose 3 elements. Okay. Now I still need to map these 2 elements, 1, 2, and these 3 elements got mapped to 5. This 1, 2 is left. No, I need to map them because this is a function. So I can map this like this, or maybe I can map 1 to 4 and 2 also to 4, and so on. We realize, okay, look carefully, that we realize that the number of ways to choose, okay, the remaining mapping is as good as counting how many functions there are from this 1, 2 set to this set 1, 2, 3, 4. I'll repeat, the choices, okay, the choices for the function, okay, choices for how this 1, 2 will get mapped among these remaining elements, okay, will be as good as counting the number of functions from this set 1, 2 to this set 1, 2. Oh, sorry. Number of ways to the number of functions from the set 1, 2 to the set 1, 2, 3, 4. Okay. So now what do you have? So how many ways are there? This set, okay, this set, if you visualize, is of size 2, and this set is of size, by which I mean cardinality, 4. So number of functions from 1 to 2, 1, 2, 3, 4 is, now we use this fact. Now number of functions from A to B is cardinality of B to the power cardinality of A. For this case, this is my B and this is my A. So 4, cardinality of B is 4 to the power 2, which is equal to 16. Now I'm not done because I need to multiply this. Okay, the product rule in combinatorics. Okay, so the answer is 5 choose 3 times 16, which is nothing but 5 factorial divided by 5 minus 3 factorial times 16, which is equal to 5 times 4 times 3 times 2 factorial divided by 2 factorial times 16. I'll cancel these. Okay, and now this is 60 times 16. Huh. Oh, okay. So there's a problem in the options. This is multiplied by 60 actually. Okay. So stone mold. There is some problem here. Should not be 60. This is 16. That is correct. Okay. Now here it should be 5 minus 3. 4 3s are 12. 12 times 5 is 60. Does anyone see a mistake here? Oh, okay. We are talking about combination, no? So here it should be 5 factorial divided by n minus r factorial, 3 factorial, times 3 factorial, which is 6. 3 times 2 is 6, 2 times 2 is 4. Yeah, which is 10 times 60. Yeah, which is 160. That's right. So this is all, sorry. This should be zeros. Times 10 each. Yeah, that's right. So the final answer is 160. There are 160 number of such functions is the answer. Okay. Does anyone have any doubts regarding this question? And this question is a bit more challenging. Okay. The key idea here is that the inverse need not be a single element. It could be a set of elements. So now the idea is to choose these set of elements. There are 3 ways to choose. There are 5 choose 3 ways to do it. And what about mapping of these remaining elements? Do a choice for that also. And but the mapping of the remaining elements is as good as the number of functions on the remaining set that we have. Using this formula, we get that 4 to the power 2 is the number of functions that map from a 2 element set, 2 size set. And okay, Albert Webster is saying, sir, please explain functions from A to B is B to the power A. Oh, okay, Albert. Yeah, no problem. So let's say you have 2 sets. Okay, one is A, one is B. Okay, the other is B. And also we are almost time here, and we are ending this. We have reached the end of the session. There are no more problems. Okay, so if you want to listen to the explanation, or if you have more questions, then please stay. Else you are free to leave. Okay, and I'll see you all on Tuesday again, 6 p.m. Okay. Yeah. Okay. Okay, Vijay. Okay. Yeah, Albert. So yeah, I was explaining this A to B. Yeah. Okay. So why is this the case, right? So what is a function? First of all, a function is an element which maps to strictly one element. Okay, and 2 elements from A can map to the same value, but 2 elements from B cannot map from the same value. Something like this cannot happen. A function cannot give you 2 inputs or 3 inputs. 2 outputs or 3 outputs, right? So now we want to count how many such occurrences are there. For example, this can be one function. and this can be another function, and so on. Now the idea is, Albert, okay, that we need to choose the pairing, how we pair them up. Okay, now what do? We do the following. um, for an element in A, okay, let me call this 1 2 3. So for an element in A, how many choices are there? I can map to the first element of B, or the second element of B, or the third element of B, and so on. For the first element A, I can have B choices. Okay. For element 1, I have size of B many choices. Right. I can choose the first element of B, second element of B, third element of B, and so on. I have size of B many choices. Okay, cardinality of B many choices. Okay, now let's say I fixed A to B, okay, I choose this for B. Let's say I told you. Okay. Now, what about the other element 2? I need to now choose for 2. The key idea is that in function, this is allowed. I can map to the same element, although I cannot map from the same element. Okay, two different outputs from the same element. Okay, like this. Yeah, this is allowed, although something like this is not allowed. Okay, two outputs is not allowed. So there, since this is allowed, I have my B's element 1, 2, 3, and so on as my choices also. So I can choose the first element of B, the second element of B, or third element of B, and so on. So it means that for element 2, this is in A, I have size of B many choices again. Okay, and so on. I do for element 3 in A, I again have B many choices, and so on until I reach the last element. For element, the last element is size of A, right? For element this in A, I have B many choices. So the total number of elements in A is how many? A, right? So until the size of A, cardinality of A. And for A, this size of A also I have like B many choices. Size of B many choices. So now just using product rule, I just simply need to multiply these choices. Okay, right? So for element A times for element first element times choices, number of choices for second element times number of choices for third element times, and so on. And this is for first element, this is for second element in A, this is for third element in A, and so on till the last element in A. Okay, and how many elements do I have? Size of A many. So this is nothing but B to the power size of A. Okay, is it clear, Albert? Let me know if there is anyone. So if fx equals f inverse of x, are solutions possible for every function? Solutions. So what do you mean by solution here? See, in a set theoretic point of view, a solution has a very different meaning. So, can you tell me what exactly you mean by solution? Because see, in from an algebra viewpoint, solution would mean all the values of x that would lead to 0, number of x values, f of x equals f inverse of x are all solutions for them. Number of x values. So do you mean like do you mean all the entire domain gets covered? Do you mean that number of x values? Okay. If f of x equals f inverse of x, yeah, this is what is called the identity permutation, right? Hmm. Okay. E to the x equals ln of x has no solution since they are inverse. Hmm. But some inverse has solution with the function. No, but see, e to the x equals ln x. Ah, okay. So you mean ln x is an inverse to e to the x. Okay, so you mean ln x equals inverse to for e to the x, right? So you mean this has no solution? Is it true? Since they are inverse. Okay, I mean, is it true that e to the x equals ln x? Okay, but again, I want to come back to it. Okay, what do you mean by solution? Um, See, the algebraic way to view it would be, solution is where the equation becomes zero, the function becomes zero. But oh, okay. So there's a solution that either f of x equals x or f inverse x equals x. Okay. So okay, I get it now. So you mean existence of such an x, right? So here, for example, does yeah, okay. So if f of x equals f inverse of x. Okay. So does such an x exist? Well, such an x necessarily need not exist, right? F inverse of x. Well, the moment that you say f of x exists, okay, it means that there is some y. Okay, so it means that if f of x exists, some x had mapped to that f of x, right? So if some x had mapped to that f of x, then if f of x exists, then obviously x should exist. So in such a case, solution could exist. But if you are asking like if so then an inverse will also exist. X is simply the inverse. But it depends on the domain also, Albert. Because like before, I was talking about this function. Okay, so here is my domain, a codomain, and here is my domain. My function f of x equals um, x square. Okay, and so what is 2 map to? 2 maps to 2 square, which is 4. What is 1 map to? 1 maps to 1. 3 maps to 3 square, which is 9. 4 maps to 4 square, which is 16, and so on, right? So if you take some element like 5 here, the inverse f inverse of 5 equals root 5, which is not an integer. So if you had taken this domain as a set of integers, then your f inverse is not defined. But if you had taken this domain as a set of reals, then your f inverse is defined. So I mean, there are these strange kind of things that will happen. But if you are talking about this specific case that f of x equals f inverse of x, then what will your function look like in this case? Okay, so should domain be restricted? Domain, yeah, domain should be restricted, but codomain need not be restricted. So your function f should work for all elements in the domain, but your function f need not map to all elements in the codomain. Okay, so I can take a really huge codomain and my function will work all right, but as soon as domain is smaller than or bigger, then my function may not work. Will solution exist for every real function? Well, in this case it will exist. Using a square root on a, yeah, because see, this side, since we are doing a square, this side will always be a positive. Since we are doing square, this will always be positive, and square root I'm doing of a positive number, then it will always be real. Unless now if I somehow this becomes negative, then square root of negative will not be real, it will be imaginary, then it will not exist. Will solution exist for every real function? No, I don't think so. So is it something related to strictly increasing function? Well, no, not really, because in strictly increasing function, you need to, as e to the x is increasing. Well, directly we cannot say it, because strictly increasing is in relation to you need to first define an order, this is greater than order, and no, I out of the bat do not see any relation with strictly increasing function. But like, coming back to your question, when f of x equals f inverse of x, your function will look like this. 1 will map to 1, 2 will map to 2, and so on, right? 3 will map to 3, and so on. Let's say the function was a natural numbers. 4 will map to 4, and so on. So this is simply how your function will look like when f of x equals f inverse of x. Okay, but strictly increasing, I don't see. Well, yeah, but it is true that this such a function which satisfies this will be strictly increasing. Yeah, such a function which satisfies this will be strictly increasing. Yeah. Because if x is if a is greater than b, okay, then f of a is nothing but a, and f of b is nothing but b, which implies f of a is greater than f of b. So if you have such a function, then it is strictly increasing. But the other way around, I don't know. Okay, we are nearing the end. Any more questions, Albert? So what are bell numbers? Okay, now this is going off topic, but I'll do one thing. I'll stop the meet. I'll stop the recording. Okay, then I'll let you know. How do I?